Professor Mohammed Hajj. And Mohammed is also the chair of the Department of Civil, Environmental, and Ocean Engineering. And he also directs the Davidson Laboratory. In fact, let me just throw in an interesting and impressive fact. And Mohammed is the PI of 2 major grants awarded this year, totaling about $7 million. Congratulations, Mohammed. And the title of Mohammed's presentation is Energy Harvesting, Microwatt to Megawatt. Mohammed, you're on.
Thank you, Henry. I'll try and finish in less than 8 minutes. I'll make sure we do that. So good afternoon, everyone, and thank you for joining. I will talk today about a couple of topics. I'll talk about energy harvesting. I'll talk about storm surge prediction in a changing climate and the role of artificial intelligence. Before I do that, let me give you a little bit an idea about my research background and how it evolved, because maybe I'll be talking about different things and one could wonder, you know, why so much breadth in the research interests and the applications. So in my PhD, I worked on hydrodynamic stability and the nonlinear stages to transition. And right after my PhD, I did some work on ship hydrodynamics and structural dynamics. And the common theme was in all of this was nonlinear dynamics. You know, nonlinear analysis, time series analysis, perturbation methods, and so on. But at the same time, you know, when I did the stability, I had to learn a lot of fluid mechanics and turbulence. So I did, you know, I branched out to doing simulation of wind loads on structures. And that is numerical simulations as well as experimental simulations. Now, if you know fluid mechanics and you know structural dynamics, you might as well work on aeroelasticity and fluid structure interactions. So in the early 2000s, I ended up at NASA Langley working on high-speed civil transport design and transonic flutter and so on. And that was a lot of fun. That later on, you know, ended up, we worked on flapping micro air vehicles. So it's all about, you know, interaction or coupling of fluid mechanics and nonlinear dynamics. That, you know, in some cases you don't want flutter to happen, of course, because it's dangerous. But if you can get flutter to happen, then you could work on energy harvesting from flutter. So, you know, and ended up working on vibration-based fluidic power energy harvesting and so on. So you could see nonlinear dynamics, fluid mechanics, and structural dynamics really constitute a lot of the background that I use. With the fluid mechanics knowledge, I recently started, you know, working after coming to Stevens on storm surge prediction, and, you know, my interest in artificial intelligence and so on, and how we could use storm surge prediction as a platform for artificial intelligence. So before I go on, I really should acknowledge that this is a lot of work that I don't know if I measure my part of it, it'll be a very minute part. But the graduate students, many visiting faculty and students, many colleagues at Stevens, Virginia Tech in the past, government labs, government agencies, and industries supported this work. So I'm going to give you a couple of examples on energy harvesting, and I want to start with powering the Internet of Things. You know, as you deploy more sensors and you want them to be wireless, you can't have wires everywhere. You can't keep changing batteries on a regular basis. And it's not only about sensing, it's about local computing as well. It's about communication, you know, receiving and transmitting signals. It's about cybersecurity. And anytime you mention one of these things, it translates into power. So you need to worry about the power levels that you require. Sometimes, you know, you need to fit these sensors in small places. So power density becomes important. Also, if you need, you know, the weight is very important. Durability is very important of those energy harvesting technologies. I mean, you don't want it to last for, you know, 2 months when you can put a battery for 5 years. And that is actually one of the biggest challenges, is how can you make energy harvesting technology durable so that we can replace batteries with it. Again, physical space is important. Sometimes, you know, you want to monitor things behind the wall or inside the wall or inside the human body, and that's very important. So some of the energy harvesting technologies include photovoltaic cells. I think Steph is going to talk about this later. piezoelectric materials, thermoelectric generators, mechanical rectifiers. And with my groups and my students and my colleagues, we've worked on most of these things. So, but I'm going to give two examples where you could see the benefits of energy harvesting, and something is. So the first one is actually about developing a autonomous water meter sensor. So many times you're harvesting energy because you're measuring energy. So you could think of the water flow as a source of energy, but also you would like to know how much water flow is there. So we came up with a device which is like this. I mean, this is commercially available. It's not a big deal, but that can act as a harvester and sensor. It's just like a turbine in here inside. So it can act as a harvester and sensor. And then it is connected here to a single board computer. I think it was an Arduino here. And then, wirelessly or through a cellular network, you could tell the single board computer here to close the circuit and charge a battery. So you close the circuit and you charge a battery for a long time. And then wirelessly, you could tell this, single board computer, stop charging and start taking data. So it disconnects in here and stops charging and it starts taking data. So we implemented this, and wirelessly we implemented it. We could charge the battery for a while, take data, charge it again, take data, charge it again, take data. And this is for different flow rates. So something like this would be important if you want to put it inside the wall where you need, like behind the wall where you're looking at a nuclear reactor or something like this. Or if you want to put it even, in a hotel to know how much a customer, how much water they're spending, so that you could, you could charge them per water they spend or something like this, the rate. I mean, it can have many applications. And this becomes more important actually if you want to do it in places where water is not available readily or is scarce. And if you want to do it also, in order as a part of a larger smart system that connects water and energy and so on. Let me talk about another application, which is high power wireless acoustic transfer. So, there are places where you can't reach where you would like to power things. I mean, if you look at a car, it probably has a few kilometers of wires in it. And, you would like to have many sensors in a car, especially with the new electric cars, automobiles or something like this. So there are all of these sensors, you would like to power them instead of connecting wires. So you could do some distributed powering through using ultrasound energy. And that is actually one of the things here. You have a transmitter in here, you vibrate this piezoelectric surface in here or disk, and then the waves propagate. They're picked up by a receiver here, and then you transform whatever you picked up here into electric power. So we did work on nonlinear effects, we did work on multiple sensing, charging multiple sensors through acoustic holograms, and we did some work on high intensity focused ultrasound power transfer systems. And again, one could say, what is this? I mean, for me, these are waves, and there is some very nice, interesting nonlinear wave propagation property that actually forces the maximum energy not to be at the focal point in here, even though you're trying to focus it. But if you try to increase the voltage out that you want, it's going to happen actually. Higher energy levels are going to happen at a distance that is upstream or behind the focal point in here. So it's a lot of interesting science and mathematics in it, and that's why something I like. Let me move on from these small things, your powering sensors or your harvesters, to a larger one where you want to power the blue economy. The blue economy, as defined by the World Bank, is about sustainable ocean resources for economic growth. We use oceans for tourism, we use them for waste management, we use them for fisheries, we use them for maritime transport, and we use them for renewable energy. So the Department of Energy's office, Water Power Technology Office, talked about powering the blue economy, empowering the blue economy through understanding what power requirements are needed for coastal and maritime markets and applications, such as the one presented here to advance these technologies. It has really two parts. powering at sea and powering resilient communities for different purposes. You could have ocean and navigation observation stations out there, offshore. You need to power underwater vehicles. You could have aquaculture in there. So you could have a lot of places where you want to power at sea. And in coastal regions, you have desalination, coastal resilience, and isolated communities that could benefit significantly from having wave energy converters. So we recently received a large funding to design actually a floating oscillating surge wave energy converter, 100 kilowatt oscillating surge wave energy converter. It has a few innovations in it. One of the innovations is in the power takeoff. We're going to have an active power takeoff mechanism. The other one innovation is in having two plates on top of a platform to be able to deploy it in deep water. There is a lot of hydrodynamic analysis and simulations in the problem, significant level of dynamics, controls, and power systems. So we're going to bring all of these things together in order to design it. And again, it's one of those things where there is significant mathematical modeling and experiments that we could work with. I'm going to shift gear here, talk about storm surge in changing climates and what artificial intelligence could do for us. Hurricanes cause a lot of loss of life, economic losses, disturbance to economic activities, disturbance to transportation, and so on. And one of the hard things about them is the uncertainty. Even if there is a hurricane in the Atlantic today, there is quite a bit of uncertainty in where is it going to land, how is it going to impact the area over which it's going to land, and so on. On top of that uncertainty, there is the impact of climate change. We design coastal structures, bridges and so on, to last for 100 years sometimes. Climate is going to change between now and then. There is sea rise level, there is rise in the sea levels, and so on. And when you're trying to predict low probability, like a 100-year event, but that's of a high consequence, then you would like to say, be able to do that. And that adds to the uncertainty that we talked about a minute ago, which is, the uncertainty due to change in temperature in the water or to a change in the jet stream and so on. So let me give you what the past, what the present, and what we can do in the future. This is a picture on the left-hand side from the Great Galveston Storm in 1900. Back then there was no forecasting, or forecasting was very primitive. Basically, some ships would report something. People would stand on the shore. They would see a storm, but they would have no idea about its destructive capabilities. So that is actually one of the deadliest storms. I think the death was of the order of 10,000 or something like this. It's very, very hard. Lots of loss of life. So what can we do today? Today, I'll give you an example here with the Stevens Flood Advisory System. We can predict what's happening over a few days on a regular basis. We do that, 24 hours a day, 365 days a year. So you could see this picture is from this morning. It's giving us a prediction about what's going to happen over the next 4 or 5 days here, if we look at it, for a station near Hoboken for the water level. Obviously, there are no significant events, but we run this on a continuous basis. But can we do this for 100 years or 50 years or something? No way. So what we need to do, we need to take a different look at it. And, of course, if you give me the hurricane parameters, I could do simulations, but that is very hard. So let me talk about artificial intelligence and how it can help. This is some work that is being performed, with collaboration with Dr. Riza Marsouli in the department and the student Mahmoud Ayad. So here we have, many of these hurricane scenarios. People can generate these synthetic hurricanes that could take place over the next, 100 years or so on. once we have these scenarios, we could run all of these scenarios using our models and predict here, let's say, the red points. And those red points are, what we can predict. But to run all of these scenarios using our own models, it will take years. I mean, this is for smaller numbers. But to run 300,000 scenarios, it will take many, many, many years to be able to run them to get water level or any kind of probabilistic estimates of storm surge levels. On the other hand, we could do, deep learning. We could do some training and then from simulations and so on. And we could go and estimate low probability events in here as you could see them. So you could see here, the return period, 100 years, 1,000 years for some of these hurricanes that we did. You could see the data points. You could see also the, prediction with the simulations, and you could see the predictions with artificial intelligence. So what's the difference? If something takes us 2 weeks to do with with the simulations, it takes us with AdCirc in this case, if it takes us 2 weeks to do it, it will take us a couple of seconds to do it with artificial intelligence. So you could see that we could reduce the amount of time that we could do things with physics-based simulation to significant, we could reduce it significantly to do it with artificial intelligence. With that, I want to thank NSF, DOE, Port Authority in New York and New Jersey, and some SEMS industry members for the support of the research I presented here. And thank you very much.
Thanks, Mohammed. And I have 2 questions in the Q&A box, but in the interest of time, I'll just have one public question that Mohammed, you answer, and the other one, if you could type offline, that would be great. And the question is, would the wave energy converter be used to power coastal cities?
Yes. I mean, yes, you could deploy these wave energy converters in shallow water as well. I think the biggest challenge is how you deploy them in deep water. It's a bigger challenge.
Okay, all right, thanks, Mohammed.
Henry, I only spoke for 7 minutes, so if you want to ask the second question, because I forget to answer it, and I'll answer it in less than a second.
Okay, so what kind of a battery is used in the autonomous water flow meter, please?
Oh, we used just, I think we used a regular battery here, a chargeable battery, but we could have used a capacitor as well.
Okay, great. Thanks very much for the exciting work.